Hi guys, this session is on internal energy from P3 of AQA. This mainly is going to be looking at what actually internal energy is, and then also looking at what happens to substances when you heat them or when you cool them based on energy. This also relates to specific heat capacity and specific latent heat also in P3. So to start with, we need to look at the basics. You'll know this from chemistry, and you'd probably studied this before GCSE as well. The kinetic model, i.e. the particle model, what the particles are like in solids, liquids, and gases. So if we look at solids, the particles there are very, very close together, which means that solids are very difficult to compress. The particles are in nice rows, they're in a nice regular structure. And they've also got very, very strong bonds between the particles, very strong forces acting there, holding the particles together, which means that solids usually have quite a high melting point, and also if you have them in a container, they will have a fixed shape. Liquids, on the other hand, liquids are very similar to solids. People do have a misconception. The spacing between the particles in a liquid and solid are very similar. Sometimes the liquid particles can be close together because they can sort of fit in these little gaps here that you would have in a solid like here. But liquids are very difficult to compress. So there's nothing like the particles are more spread out really than a solid. The particles do have some very weak interactions, or weak bonds holding them together. But they're not as strong as they are in a solid, which means that a liquid can flow. Hence it is a fluid, so you can pour it, and when you put it in a container it will fill the bottom of the container. And in gases, the particles have a lot of kinetic energy. Compared to a liquid, they have some kinetic energy. In a solid, not much. Solid, they do move, they sort of vibrate on the spot. Liquids, they move around each other, but gases, they move around with quite high speeds, randomly colliding into each other and the walls of the container that they are contained in. The bonds between them are very weak, if not negligible. They don't really exist. And there's lots and lots of space in these particles. So the space gives rise to the fact that you can compress a gas, and these weak forces means that gases can be poured and they will fill the shape of the container they're in. So if we come on to internal energy, when we look at what internal energy is to do with the energy that these particles have. So if we look at, for example, all these particles in solids, liquids, and gases, they all have kinetic energy. Kinetic energy, essentially the energy due to movement. So in solids, they have some kinetic energy. Liquids, they have more kinetic energy. And gases, they have a lot of kinetic energy. And it's also to do with potential energy. So potential energy is due to the energy stored. Now, in solids, they have a little potential energy. Liquids, they have more. And gases, they have even more. It's quite hard to explain what's going on with potential energy. I would imagine it kind of like a spring. So if you think of like a solid, when you're heating a solid, what you're doing is you're turning into a liquid by breaking those bonds. The energy used to break those bonds is now stored in the particles. So it's like saying you're trying to tear apart something like two magnets, and you have to put that energy in. The potential energy is still there. The energy in those magnets are still pulling the particles together. So when we get to something like a gas, they have even more potential energy because we've broken even more bonds in order for the particles to move around each other. So potential energy is to do with energy stored within those bonds, and if you have something like a gas, that has got a lot of potential energy because we've overcome those bonds. So internal energy is essentially the sum of these. It's the total kinetic energy and potential energy of the particles. The kinetic energy relating to how fast the particles are moving, potential energy related to the energy stored in the bonds, saying that gases have a lot of energy stored, hence they don't have bonds holding them together. So that is how you define kinetic and potential energy, internal energy, the sum of the kinetic and potential energy in a substance. So if we then get on to this is how internal energy relates to the whole stuff. You may have done this experiment, you may see this experiment to do with heating a substance. The usual one that we do in class is to do with stearic acid, but sometimes we do with things like butter and chocolate. But let's say you're doing an experiment and you had a substance and you were heating it up over time, and you're going to measure the temperature at regular intervals. what would that graph look like? Well, it obviously depends on the substance, but let's say I had a substance and I heated it and it was a solid at room temperature, and I heated it, I would get this graph here. Now, what you can see happening if we look at the different stages is that to start off with, let's call this sort of stage 1, the temperature does increase from 20 to 50. At stage 2, the temperature remains constant. Stage 3, the temperature increases from 50 to 80 degrees. And then stage 4, temperature constant. And stage 5, temperature increases again from 80 to about 100, just over 100. So what I want to do is explain what's happening. So what we've got here, to start off with at stage 1, this is a solid. And what we're doing is we're heating up a solid. When we're heating up a substance, we're transferring energy. Now at this stage, when we're transferring the energy, what we're doing is we're transferring the energy as kinetic energy. So when we're transferring kinetic energy, what we're doing is we're increasing the speed of the particles here. So at stage 1, we're increasing the kinetic energy. That is what essentially temperature is. Temperature is like a mark of individual kinetic energy. So if you have an increase of temperature, you have an increase in kinetic energy. Now, stage 2, the temperature seems to remain constant here. That's because at stage 2, what we're doing is we're not transferring the energy as kinetic energy anymore. We're now transferring it as potential energy. So here at stage 2, the potential energy is increasing because what we're doing is we're increasing the potential energy of the solid. We are breaking the bonds between the particles in a solid. So essentially what we're doing, if we're breaking the bonds between the particle and the solid, we're melting. We're turning the solid into a liquid. So at stage 2, we are melting. Now, when all of that has happened, when all of the bonds are broken, we stop transferring the energy as potential energy, and the energy that we're now transferring is going to be turned into kinetic energy. So at stage 3, you can see the temperature is increasing there, the kinetic energy is going to be increasing. So now we're a liquid. What we're going to be doing is we're going to be making those particles move around faster and faster and faster. Stage 4, what we've done is we've made those particles move as fast as we can. We're now turning the energy we're transferring into potential energy again. So here the potential energy is increasing. And again, temperature is not changing. We have a change in state. So now we're going from liquid to gas. Now that change in state is boiling. Maybe asking about this thing called evaporation. Evaporation is where a substance changes from a liquid to a gas, but it can happen at any temperature. Boiling is where you have enough energy for all the particles to do that, i.e. when the particles have lots and lots of kinetic energy. So then we get to the point which the potential energy has increased enough. We've broken all the bonds even more. The particles in a liquid do not really have those strong forces of attraction between them, and it has turned into a gas. And if we keep on heating the gas, we're just going to be transferring the energy as kinetic energy. So here, the kinetic energy is going to be increasing once more. And there is another state change after this, where you go from a gas to something called a plasma. So you would see another state change, but we don't tend to complicate it like this. We just normally have in the two state changes, melting and boiling. So just to recap, where you have a change in temperature, that is where the kinetic energy is changing. So in this case, the temperature is going up, the kinetic energy is increasing. Where you have a temperature that is staying the same, that is a change of state. Now, it depends on where exactly this change of state is happening. You need to make sure you're aware of it could be melting, it could be boiling. You've got to look. So for example, if you look in this, I can tell that number 2 is melting rather than number 4 because melting would happen before boiling. So number 2 has to be melting, number 4 has to be boiling. But if you had a graph like this and you couldn't see anything else, you might not know what that is unless you know that here is a liquid and here is a gas. So just be careful. If you were literally just given a graph of temperature against time and it said what's happening there, you've got no idea if it's melting or boiling unless they give you any other information. But the key thing is there is a change in state. So temperature changes, kinetic energy changes. Where you've got the temperature remaining constant, the potential energy changes, and there's a change of state. So you could actually have the converse here. You could have the opposite, where the graph is actually the other way around if you've got a cooling graph. So you might have something like this, where you've got time here and you've got temperature here. Again, what will happen is if it's going from a gas, it will then condense, and then it will cool down, and then it will freeze, and then the temperature will just decrease even further. So we've got the same thing here, where let's look at the changes of state. Here, that is condensing. Here, this is freezing. So this is a solid here. This is a liquid here, and that is a gas here. So here, the kinetic energy is decreasing. Here, the potential energy is decreasing. Kinetic energy decreases. Potential energy decreases. Kinetic energy decreases. You can see the pattern related to the other one. So when you're cooling something, you're decreasing the energy. When you're heating something, you're increasing the energy. We want to relate this, though, to internal energy. Because if you remember, internal energy is equal to the sum of the kinetic energy and the potential energy of the particles. If you look at the graph on the right, when you're heating a substance, you're either changing the kinetic energy or the potential energy. So what you're always doing is you're changing the internal energy. It's just that you're changing different parts of it at different times. So at stage 1, you're changing the kinetic energy. Stage 2, you're changing the potential. Stage 3, you're changing the kinetic. Stage 4, potential. Stage 5, the kinetic. Either way, you're changing the internal energy. So when you're heating up a substance, you're always increasing the internal energy. Again, the converse, when you're looking at cooling something, when you're cooling something, you are decreasing the internal energy. It just might be that you're decreasing the kinetic or the potential. Just remember that when you have a change in state, the temperature remains constant and you're changing the potential energy. And when you have a change in temperature, you are changing the kinetic energy. Hope that helps. See you next time.